Welcome back. In the last part of this section, we talked about the definite integral, and we'd ended off with the observation that if we have a function that is continuous, if it's non-negative, then the definite integral represents area. And that's exactly what we have here with the following theorem. If we've got a continuous and non-negative function, and we're looking for the area between our function f and the x-axis, between x equals a and x equals b, then the area is that definite integral. So as an example here, I've got myself the question of express the area of the region bounded by this line, y equals 5 minus 2x, the x-axis, the y-axis, and the line x equals 2. And if I wanted to express that all as a definite integral. So first thing, if I'm thinking about this as being my function f of x, it definitely meets the condition of being continuous, and it is also non-negative. We can see that on the graph here, that between 0 and 2, my straight line y equals 5 minus 2x is not below the x-axis. And we are looking for a region bounded by that line and the x-axis, and it's between two vertical lines. It's between the line x equals 0 and x equals 2. So according to the theorem, the area that we're looking for should be the definite integral from 0 to 2 of f of x, 5 minus 2x dx. And if I wanted to, this is not a hard one for me to figure out as far as the area goes. It didn't ask me to do it, but I could without too much difficulty because I recognize that the shape that I have here is a trapezoid, that the height of the one parallel side is 1 unit, the height of the other parallel side is 5 units, and the perpendicular height of my trapezoid is 2 units. We know for the area of a trapezoid, the area is 1/2 top plus bottom, so 5 plus 1 times height times 2. So this area should be 6, and this is found just using the area formula for a trapezoid. So still we're going to put a pin in this. At some point we will learn how the connection between definite integrals and indefinite integrals, and we'll see that actually there's an easier way. But for right now, if we're looking for a definite integral, and if it represents an area, and if it's an area that we know a geometrical formula for, then we can go ahead and find that definite integral. So for example, this function that I'm looking at, this square root of 9 minus x squared, if you were graphing that, that would be a semicircle with a radius of 3. And if we're looking at the integral from 0 to 3, that would be all of the area that's in that 1/4 of my circle. So if I'm looking for the area then of that quarter circle, that is 1/4 of pi times the radius squared. Or in other words, I said 1/4, but I wrote 1/2. There we go. 1/4 times pi times the radius squared, or 9 pi over 4. And that's because I recognize that the definite integral from 0 to 3, since my function is continuous and non-negative, then that represents the area under the curve between 0 and 3. And that's the quarter of the area of a full circle. For part B, same sort of thing. The line 6 minus 2x, I've graphed it here, and you can see that if I'm looking from 0 to 3, again, I'm looking at the definite integral for a part of the graph where the curve is non-negative, so where it's above or at the x-axis. And so if I'm looking for the definite integral from 0 to 3, well, then that would be the area under the curve from 0 to 3. And we can see that that's just the area of a triangle. And we know area of a triangle formula is 1/2 times base times height. The base is 3 units and the height is 6 units. And so we wind up with 9 as our definite integral. Now, some properties that we can establish right away with our definite integral is number one, if we've got our function is defined at that point, x equals a, then if you're looking at a definite integral from a to a, then f of x, definite integral of that would be just 0. And that if we switch the order of our limits of integration, that switches the sign. So in other words, whatever the integral from a to b is and the integral from b to a is, they'll be opposites in sign. They'll be otherwise equal, but just opposites in sign. And we also have a nice little property here, the additive interval property, that says if you are looking at a definite integral from a to b, that you could look at the definite integral going from a to some intermediate value c and then continuing on from c to b. And here we don't have to have any restriction that c is in the middle. So for example, if you were looking at a definite integral from 1 to 3 and you decided to go from 1 to 5 and then from 5 to 3, that would indeed work. This is, of course, provided that your function is integrable on all of those intervals. So if it's integrable from 1 to 3, from 1 to 5, and 5 to 3, then for sure that would be true. So that's actually a fairly strong property to have. So we don't even need a to be less than b for this property to occur. So any three values, integral from a to b is same as integral from a to c followed by from c to b. So we're going to use that here in action. So somebody has figured out for me that the definite integral of sine from 0 to pi happens to be 2. And I'm looking at the definite integral from pi over 4 to pi. Apparently that is 1 plus 2 root 2 over 2. So the question is, what is the definite integral of sine from 0 to pi over 4? So here I'm going to use the theorem that we just finished with. It said that if you are looking at the definite integral from 0 to pi, that's the same as going from 0 to pi over 4, followed by going from pi over 4 to pi. So using pi over 4 as our little intermediary value. And now I can put in what I know, which is this. I'm looking at the definite integral from 0 to pi over 4, so that's what I'm looking for. But I know the integral from 0 to pi is 2. And I know that the definite integral from pi over 4 to pi is 1 plus root 2 over 2. So now I can solve, and bringing the 1 and the 2 root 2 to the other side, or root 2 over 2 rather, I'll have that the definite integral from 0 to pi over 4 of sine x dx is 1 minus root 2 over 2. So again, just like we had for summations, as we also had for limits, as we had for differentiation, for definite integrals as well, we have a constant multiple property and a sum and difference property. So if you have two functions, if the integrals exist of f and for g, then they will exist for k times f and k times g. And f plus g will have an integral, and f minus g will also have an integral over that interval. And then we can treat things basically as you expect. So constant times a function for the definite integral, you can take that constant outside. If you have two functions that are being added or two functions that are subtracted, you can split it up into two definite integrals that are being added or subtracted. So here I've got some facts given to us. I know that the definite integral of 1 is 1, of x it's a half, and of x squared it's a third, and these are all definite integrals going from 0 to 1. So if I'm looking at this definite integral from 0 to 1 of 9x squared minus 6x plus 7, I know that because of the definite integral properties that I can split that up into three terms. Definite integral of 9x squared minus the definite integral of 6x plus the definite integral of 7. And I also know that 9, 6, and 7, those are all constant multiples, so those could come outside. I'd have really 9 times the definite integral of x squared minus 6 times the definite integral of x plus 7 times the definite integral of 1. And now I can use what I've been given. I've been told that the definite integral of x squared is a third. The definite integral for x is 1/2. And the definite integral of 1 is 1. And then basically I'm finished. I can say that my definite integral then should be equal to 7. A couple of little properties that we have, which is that integrals preserve our inequalities. And by that I mean if you have a function that is greater than or equal to 0 for that entire interval, then its definite integral will be greater than or equal to 0. And it's also true for the reverse, that if f is less than or equal to 0, then that means the definite integral of f would also be less than or equal to 0. Again, if it's less than or equal to 0 on that entire interval, then the definite integral over that interval will be less than 0. So that's what we mean by it preserves the inequalities. Same thing with if you have two functions. If one function is less than another over that interval, then the definite integral of the one function is less than the definite integral of the other. And of course, the reverse is also true. If f was greater than or equal to g, then the integral for f would be greater than or equal to the integral for g. So again, it's preserving our inequalities.